Welcome to the first video in the series on using Activeloop and Deep Lake as a data versioning and data exploration tool. In this first video, we're going to have a look at how we can use the Activeloop web interface to explore the datasets and to understand what's in it. And then we're going to use that, look at using the SDK, the Deep Lake SDK, to actually use the images from the dataset in a training environment. So first we're just going to play around a bit with the SDK and see how it works. And then we're actually going to use it to train an MNIST digit classifier using scikit-learn. So the first thing that we're going to use is that we're going to Activeloop.ai. So this is the actual tool that we are going to use. And you can log in here, and the first time, if you haven't created an account, you can, for example, register using your GitHub account. So that's basically a one-click sign-on. When we get here, we can see that there are different datasets. And some of the datasets are from Activeloop, and some are public datasets, which are uploaded by other organizations and published. So we're going to start with looking at some of the datasets uploaded by Activeloop. And here we can see that we have different modalities of the data. We have some image datasets, typical photographic images. We have an MNIST dataset. We have faces. We have different X-ray images. And we have audio images. So let's start with taking a look at the audio images, how it can look like in this case. So what we see here is on the left side, we see a short explanation of the dataset. We can click on the structure and see what kind of data is in the dataset. So we have two different tensors in this dataset. We have the actual audio clip, and we have the genre, which is the label. And we can click the info on the genre and see what different class names are there in this dataset. And we can also see the different properties about the tensors. And we can see the length of the tensor is the number of samples in the dataset. We can also see that up here. And here on the right set, we can actually explore the data. So we can pan around and see the different audio clips. We can see the label up to the left here. And we can always click this I button up here and see the different tensors and how they are visualized. So we have the audio and we have the genre. If I remove this, we can see that the genre is removed. And I can click on this and actually play the sound. So this was yes, and I can press on it and also see the size of the data, and I can see the different the label again here. So let's remove that. So let's pan down to another place and see how we have some country music. And I can also use this window up here to go to a specific index. So if I want to go to index 0, I can type 0. Okay, so let's go back to the datasets and see how it can look like in another dataset. So let's take this chest X-ray dataset. So here to the right we have the X-ray image, and we have different labels up here, so we can see what tensors they are. We have something bounding boxes, doesn't seem to be anything in this one. We have the metadata, so that's this one and those ones. We can hide them if we don't want to see them. And we have the findings, which is the medical condition. So we can also hide that if we just want to see the image. We can add a medical condition again. And of course, you can also see in the structures here what different tensors we have. So we can see that it's a lot more tensors on this data set, a lot of different metadata. And we can look at the findings here, which is the medical conditions, and we can see what different kinds there are. There's a lot of different medical conditions that I don't know much about, but I recognize pneumonia. So let's look at how does images with pneumonia look like. It can be interesting to see if I can see any difference, or if it's too tiny difference to see. So I could, of course, scroll around here until I find something with pneumonia. But we have 86,000 images to pan around between. So instead, we can run a query on the data. And this is unfortunately a function that is only available in the free version on the datasets uploaded by Activeloop. So if you use the other public datasets or datasets that you yourself have uploaded to your private dataset repository, then you will not be able to do the queries unless you pay for the subscription of the Activeloop tool. But basically, this is a SQL-inspired search box. So we can type example queries here and see some different examples. And we can actually click this one. So this is the way we can show all images that contains the finding fibrosis. But I wanted pneumonia. Let's execute this query. Now I have everything not pneumonia. So here we have all the images with pneumonia. So now I can pan around and see what does these images actually look like. And then we can go back to where it's not pneumonia. And we can see if there is any difference. So this is a little bit about how we can use this tool to actually explore the data by searching. And perhaps a more interesting example is if we take the ImageNet dataset. And we can also go to structure here and look at the class names. We have great white sharks. I want to see images of great white sharks. So I'm going to run a query. Select everything where contains and labels is the name of the tensor in this case. Here it's important to use the single quotes for labels. So here we have lots of images of great sharks. So one of the things we can see here is that some of the images has bounding boxes for the sharks, while some of them doesn't have it. So that would be one interesting finding if we were going to use this data set to actually train an object detector for great white sharks. That not all of them actually has bounding boxes. Some are just labeled as an image classification label. So let's continue to our example of actually using this to use the dataset in your Python code. So we're going to start with using MNIST. And this is, of course, digits, where we have a classification on what digit in it is it in the image. So I'm going to open a new tab and open Colab, Google Colab, and create a new notebook. I'm going to name it with Deep Lake. Deep Lake is the name of the Python library that is used to as an SDK to the Activeloop datasets. So Activeloop is the platform with a web interface, and the Deep Lake is the library. So in Colab, we usually see that most or very many of the machine learning frameworks are already installed. But if we do import Deep Lake, we can see that this is not the case for Deep Lake. So we actually need to also install Deep Lake. Now we have Deep Lake. So the way that we load a dataset is with a load method. And this takes the specifier of the data lake or the dataset. And we can find it here in the summary. So we can copy this specifier and paste it here. Now we have the data set. So what this is now is actually not the images that are downloaded. It just downloaded metadata about the dataset. So we can do length of dataset and see how many samples there actually are in the datasets. But the samples themselves are not downloaded. So each one of these tensors, which we can see in the structure, they are stored now as a reference to the server. So if we do ds.images, I can index the 0th image here, execute this. We said that this is a tensor at index 0, but it doesn't give us any data about it. The same if I do for the labels. We see that it's a label at index 0, but it doesn't tell me what data. So I can go to index 0 here and see what image we're actually working with now. So this is a 5. So now if I actually want to get this label, what we need to do is to call a NumPy method on it. This will actually download this specific label for the 0th index. So another way we can do this is that we can download all of them in one go instead of downloading each label every time we need it. Because we can see that we have 60,000 images. And if we're going to download each label each time we need it, we will need to do 60,000 downloads just for one epoch on the dataset, which will be very slow. And the labels are not large, so we know that 60,000 labels will fit in our primary memory. Instead of calling it on the 0th index, we can call it on the full label array. And now instead have a NumPy array local on our computer with all the 60,000 labels. So let's look again at the images. We know now that label 0 is a 5. So let's verify that the 5th or the 0th image actually is a 5 also. So to visualize the images, we're going to use hello, or more specifically, the image class. And as we learned in another video on the crash course to computer vision, if you haven't seen it yet and don't know how these things works, take a look at it. It's a 5-part video with a crash course for doing machine learning with Python and scikit-learn. Here we learned that we can do the from array, and we need an NumPy array. And in this case, we can use datasets, images, and the 0th image, and we should visualize it as a grayscale image. And now I actually see that this is a deep lake tensor. So now we also need to call the NumPy method to actually download it and create a NumPy array from it. And here we can see that we have the 5. This is the same 5 as we have at index 0 here. So the important thing to understand here is that we're dealing with a streaming dataset. That is, the images is stored on the server until we explicitly ask to get that specific image. So if we want to iterate over the dataset, there are 2 different things that we can do. So in this case, perhaps I want to calculate the mean value for each image in the dataset. If I do it like this, then we will iterate over the local metadata. And for each reference to an image, we will download that image and calculate and print the mean value for it. And of course, we need to import NumPy. So this streaming array is very useful if the images are large, and for example, you're working on a laptop. Then perhaps your primary memory doesn't fit all the images in the dataset. So we need to actually download each image as we want it. And if we want to access the same image multiple times, then we can download it multiple times and remove it in between, so we don't need to store the states. But the other option is that we can call NumPy directly on this one. So this will actually download all the images in one go to one large NumPy array. And then we iterate the element in that NumPy array. So if you have enough memory on your system to actually store the full dataset, then it will typically be faster to download it all in one go and then use it. But on the other hand, it's more latency because we first need to download everything and then we can start using it. While if we're streaming the data, then we can use it, use the first sample as soon as they are downloaded, while the later part in the dataset continues to download. So that is something that you can experiment with, what is most beneficial in the specific use case you're working with. So enough of exploring the API. Let's move on to actually implementing a classifier for these MNIST digits. So what we're going to use or do now is that we're going to go to the AI/ML principles exercises folder. And in this one, we will find the CV crash course, the computer vision crash course. And here we have a digits classification notebook. So what we did in this notebook was that we used sklearn, and we used the digits datasets, which is included in that library sklearn. So this was tiny 8 by 8 pixel images of different digits, and we tried to classify them with an support vector classifier, a support vector machine. So let's open this in Colab, and we can save this as a new copy. So I'm going to save it in the same repository. And of course, if you haven't already done it, you can fork this repository by pressing the fork button in GitHub and get it on your own GitHub account. And then you can create your own branches and upload your own data to it. So that's a good way of versioning your notebooks. I'm going to create a new folder called Activeloop Deep Lake, and digit classification sklearn is still valid, and the commit message will be copy of the sklearn example. Okay, so now this is saved. So let's open it again in Colab. And so the datasets from sklearn, we're not going to use that anymore, since we will use Deep Lake instead. So as we did before, we want to import Deep Lake, and to do that, we need to pip install Deep. Oops. Pip install Deep Lake. Hit Shift Enter to run this cell, or you can of course do it from the menu up there. So now we got an instance allocated, and it will install Deep Lake and import the libraries. Okay, so now it comes to actually loading the dataset. And in this earlier example, we just had one dataset, which we used both for training and testing. So there we used the sklearn helper function train test split, which splits the data in an 80-20% ratio between training and testing. But if we go back to the Activeloop page here, we can see that this is actually MNIST train. And if we just search for MNIST, we can see that there is one MNIST train and one MNIST test. So this is typically the way that Activeloop divides its dataset, but that it divides them before uploading them. And the benefit of that is that it's sometimes easier to use it that way. And you also get the same split each time. So if you compare on the test data sets, you know that the test and train split are the same between your different experiments. So heading back to this classification notebook, instead of loading the digits from the sklearn dataset, we're going to have two different datasets. One D is train, which you do get by deeplake.load. The user account that the dataset is from is Activeloop, and it's MNIST train. And we have the second one, which is the test dataset. two datasets, and then verify that we have the length of DS train, and we have length of DS tests. We can see that we have 60,000 images in training dataset and 10,000 images in test datasets. So the visualization of the images, we did it in the other notebook, so let's just remove this for now. And we can actually, let's undo this. So in the old dataset from sklearn, we saw that the maximum values was 16. So all the images was floating point 0 to 16. And if we actually look at how the images look like in this dataset on Activeloop, we can see that the maximum is 255. And we can also, of course, print the type of it. So we see that this is an unsigned integer 8. And the shape is 28 by 28 instead of 8 by 8, which is what was in the sklearn datasets. So in the sklearn dataset, we, since we're going to use a support vector machine, we want a flattened array. It doesn't have any understanding of spatial distribution or the second dimension. So instead we're flattening everything. The 8 by 8 images was flattened to an 64 long array. And now we're going to have 28 by 28, so 784 pixels long array. So the issue now is that this dataset is still not downloaded. And if the dataset was large and we couldn't download all the images at once, then we would need to do some generator type of function that rescale the images on the fly as they are downloaded. And that will be later in the exercise. But for now, this dataset is quite small. It's just 28 by 28 pixels. So we can download everything. And we saw before that the way to do that is that we do dataset.images and we call the NumPy method. So calling this will actually download all the images to our RAM memory and create one giant NumPy array of it. And then we can reshape this. And the number of samples is the length of DS train. It should also be DS train. If we do like this, now it actually goes through and downloads all the images and creates an NumPy array from it. And then it reshapes the array. And we see that we get 60,000 images, and each one is a 784 long array. So let's go on to training the model. Before we use the train test split, we don't need to do that now since we have one DS train and one DS test. They were already split up in the Activeloop data hub. So I actually did a flattening, and we split them into X train and X tests. So instead of this, let's do X train. Copy this because we didn't save the result. So we create a NumPy array with all the vectors for all the images in the training datasets. Then we do the same for X tests. run this. And we see that here we also have y-train and y-test, which are the labels. So we can do the same here, that y-train is dstrain.labels. And we could actually just pass in this tensor to sklearn, and that would work. But then it would download each label each time we access it. And doing 60,000 downloads will be slow. So instead we also prefetch these labels. And we do the same for the test data sets. This cell, which we now have replaced with these two. Okay, so now we have the x-train, which is 60,000 times 784, and we have the x-test, which is 10,000 times 784. We can still do this if we want to. Image is not defined because we have to and since we saw before that the old ones was 16 maximum value, so to visualize it we wanted 0 to 255. But this images in the Activeloop hub are already 0 to 255, so we can remove this rescaling. And they are already 8-bit unsigned integers, so we can also remove that part. And we shouldn't reship it to 8 by 8, but instead 28 by 28. Here we can see a test image. So next, let's go on to the training. But before we do this, we need to know something about how the support vector machines scale with the number of data samples. And I think support vector machines are quite good for high dimensional data. So in this case, we have dimensionality of 784 on our input data, and we have 60,000 samples. And if I remember right, the support vector machines scale quadratically with the number of samples and just linearly with the number of dimensions. So that means that they are quite efficient for high dimensional data, but a bit problematic when it's a lot of samples. So since I don't want to wait forever now, we're going to subsample just a few images from the data set. So we're going to use NumPy for this. And we could do some random selection of the training labels or the training data and the labels. But then we wouldn't know which ID it is in the Activeloop index, which means that we couldn't find them here again. For example, we know that this image that we visualized was index 100 in the test data set. So this is the test data set, and let's go to index 100. So now we can find it here too. And we don't want to lose that information. So instead what I'm going to do is that we're going to create an array with the indexes of the images that we're going to use. So we can do that with NumPy random choice, and the numbers that we're going to choose from is between 0 and the length of the training data. And we're not going to use to replace data within it. And we also need to specify how many samples we should have. So let's use 1,000 samples to train on, just because we want it quick. So this is now just a vector with 1,000 different indexes between 0 and 60,000. So let's go on to the training. And in the last time we actually specified this hyperparameter. I think in this case we have higher dimensional data, so we can just try to leave it empty and it will be automatically estimated by sklearn. Instead of training on all the training data now, we're just going to select the training indexes. So we select 1,000 randomly selected images from the full training dataset. And of course, we need to select the same training labels. So that was quick. Now we have a trained model. So let's try to predict some of the test data. And we print the test data values. So now we see that this is actually a 2D array, even though its first dimensionality is, or the first dimension is just 1. But we could do flatten on this one. And instead, we will have the same problem in multiple places. So up here, when we do Y train and Y test, we can flatten them directly. And this shouldn't affect the training of the model. But let's verify we can retrain the model, and we repredict the test data set. We show the actual correct labels for these samples. So we see 7, 2, 1, 0, 4, 1, 4, 9. We have 1, 6 predicted as 5, and 9. So it seems like we have 9 out of 10 correct. Verify it with this. So very roughly 90% of this small sample. So let's now use the classification report to actually get the true or the result on the full test data set. So we can see that we have 92% accuracy. And we can also plot our confusion matrix. We can see what kind of confusion we're making. So we see that most of them are correctly classified. The diagonal 0 is classified as 0, 1 classified as 1, and so forth. But we have 25 here that should be 7, but they are classified as 2. We have 38 that should be 8, but are classified as 5. And we have 63 that should be 4, but they are classified as 9. So 92% accuracy. We can, just for fun, try to train on 10,000 samples instead. So now we see that the training takes significantly longer time, even though we just increased the size of 10. It feels like it was more than 10 times. And that's what we expect if it is quadratic to the number of samples. So now we can see that we actually have 96% accuracy at this point. So saving the model to disk and using it should be exactly the same as before. So if you're interested in that, instead go and watch the computer vision crash course. So this was the first video on actually using the Activeloop datasets to train a classifier or machine learning model. So stay tuned for the next videos.